Hello, our students, life science and general science at Amal Education Institutions. I am the physics advisor intended together with your teachers to end the program for you this year. For this, I select the theme that carry the title Atomic Nucleus. At the end of this chapter, you are able to understand the composition of any atomic nucleus, the nucleoids, isotopes, calculate the dimensions of any nucleus, calculate the mass and the density of an atomic nucleus, understand the relation between the mass and energy according to Einstein's relationship, and deduce from it the mass defect and the binding energy. Understand the stability of an atomic nucleus. Let's start with the composition of an atomic nucleus. Every chemical element X has a nucleus formed from a nucleons, in which there are Z positively charged particles that we call them protons. So we say Z is the charge number. And identical neutral particles called neutrons. A is nothing but the sum of the protons and the neutrons. We call it is the mass number. A equals Z plus M. This is the equation here. The symbol for the chemical element nucleus is XAZ. As examples, we may have H11, H21, C12-6, C14-6, U23592. This is a design for the proton, the neutron, and the nucleus. They are all look for the design of the atomic nucleus. The diameter of the nucleus is about 10 minus 8 meter approximately. It is nothing but 1 fermion, 10 minus 15, the diameter of the nucleus. The diameter of the nucleus is 10 million smaller than that of the atomic diameter, and the nucleus, as we know, till now, is composed from protons and neutrons. Certain researches may lead to other particles. The nucleoid. A nucleoid of any chemical element X is the set of nuclei having the same mass number A and the same charge number Z. The nucleoid AG147 nucleoid contains Z, which is 47 protons and N equals 60 neutrons. Isotopes of a chemical element is the set of all nuclei having the same charge number but different mass number, and hence the difference in number of. We have some isotopes that we have. Hydrogen H11, it contains 1 proton and 0 neutrons. H21 is nothing but deuterium, it has 1 proton, 1 neutron. We have H31, it is called tritium, 1 proton and 2 neutrons. We have the carbon. Carbon, we choose 2 isotopes, C12-6, C13-6. The number of protons is 6 in both isotopes, but the number of neutrons are either 6 or 7. Uranium-235 is nothing but 92 protons and 143 neutrons. Abundant natural uranium is composed of 99.3% uranium-238 and 0.7% fissile isotope uranium-235 that is used in nuclear. The dimensions. It is admitted that the nucleon, either protons or neutrons, is a shape of a sphere and of radius 1.2, 10 minus 15 meter, 1.2 fermion. The volume V0 of such a sphere is 4 over 3 pi R0 cubic. Any nucleus XAZ has A nucleons. Its volume Vx is 4 over 3 pi R cubic. It is equal A times V0. So we look for the radius of the nucleus, R equal R0 of the nucleon, times the mass number A raised to the power 1 over 3. As example, uranium-238 has a nucleus 1.2 fermium times 238 to the power 1 over 3 is 7.44 fermiums, while that of iron 56, its radius is about 4.6 fermions. The mass of the nucleus, knowing that the mass of the proton and that of the neutron is approximately that of the atomic mass unit. It is 1.710 minus 27 kilogram. So we can say that the mass of the nucleus approximately is 8 times the mass of the atomic mass unit. The density of the nucleus, XAZ, is nothing but its mass over its volume. Related to the mass number of both the mass and the volume, we say that the density is nothing but the mass of the nucleon over the volume of the nucleon. But this is constant. So we say that the density of the nucleus is constant. Its value is 2.34 times 10 to the power 17 kilogram per meter cubed. Very, very heavy. Note that the density of the nucleus is independent of the mass number. It means that the density is the same for all atoms. The density of the nucleus is maximum as it is at center and decreases as we move outwards from the nucleus. Example, the nucleus, you have to treat it. The nucleus Aluminium 2713 is an aluminum isotope. Calculate the radius R, knowing that the radius R0 of the nucleon is 1.2 fermium. Out of the table below, which nucleus have double the radius of aluminum? The mass units. Let's look for the atomic mass unit, which is represented by U. Definition: the atomic mass unit required in the official exam. The definition: the atomic mass unit U is the mass of 1 over 12 of mass of carbon-12 atom. This means that one atomic mass unit is 1.66053 10 to the power minus 27 kilogram. To calculate this relationship, we have the mass of the carbon-12 atom is nothing but the molar mass over Avogadro's number. So it will be 19.92636 times 10 to the power minus 27 kilogram. As we know, U is 1 over 12 of the carbon-12 atom, so it will be 1.66053 times 10 to the power minus 27, approximately 1.710 mol power minus 27 kilogram. Einstein's mass energy equivalence. You have to understand that Einstein find a relation between mass and energy. Mass and energy are two different forms of matter. We either find matter as mass or energy. They are related by relationship. The energy equal the mass times c squared, where m is in kilogram, c is in meter per second, speed of light in vacuum, and d is the energy in joule. We can represent the energy expressed in mega electron volt. Then we look for the energy. The mass m will be as mega electron volt per c squared. That is expressed by this way. 1 mega electron volt, as you know, is 1.610 minus 13 coulomb times 1 volt, Q times U, equal 1.610 to the power minus 13 joule. So the mass of 1 mega electron volt is nothing but 1.78 2 times 10 to the power minus 30 kilogram. Comparing it to U, we have 1 U. It is found to be 931.5 mega electron volt per c squared. So we have 1 U given in the official exams. I want from you to treat this simple exercise. Calculate the volume of oxygen 16.8, calculate the approximate mass, deduce its density. Okay? As example, comparing the mass of the proton to that of the atomic mass unit is 1.00728 U, while that of the neutron, the mass of the related to U is the mass of the neutron divided by the mass of U. We have 1.008665 U. So they are approximately that of the mass of the 1 U atomic mass unit. This is a table representing the relationship between the atomic mass unit in kilogram and mega electron volt per c squared. That the mass of the electron, proton, and the neutron. Nothing is to memorize. All should be given. The mass defect. The origin of the mass defect is caused by the conversion of the mass into energy when the nucleus is formed. Definition: the mass defect is defined as the difference between the mass of the atomic nucleus and the mass of the sum of its nucleons. Delta M is nothing but Z times mass del protons plus M times mass del neutrons minus mx. As remarked, nuclear reactions are the sole method of the loss of mass in a nuclear reaction. If we look for the helium nucleus composed of 2 neutrons and 2 protons, before forming the nucleus, the nucleons have total mass 4.032 U, while after they form the nucleus, it will be 4.0015 U. There is a mass defect which is 0.0305 U. Binding energy. We define the binding energy of an atomic nucleus. It is the energy needed to break the nucleus down. Formula: according to Einstein's mass energy relationship, E binding is nothing but the mass defect times c squared, where the mass defect is nothing but Z mass del proton plus N mass del neutron minus mx times c squared. Stability of an atomic nucleus. The degree of stability of an atomic nucleus is the energy needed to extract nucleons out of it. To know the more stable nucleus of the isotopes of a chemical element X, it is the one whose binding energy per nucleon is the greatest. We look for the binding energy per nucleon to study the stability. Now, the formula that we have to use, E binding per nucleon, is nothing but E binding of the nucleus divided by the mass number. As example, the mass defect and the binding energy of deuterium. Let's calculate the mass defect and the binding energy of deuterium, knowing that the mass of deuterium is as such, and we can turn it into mega electron volt per c squared. So for deuterium, Z equal 1 and A equal 2. The mass defect for the deuterium is delta M is mass del proton plus mass del neutron minus M the deuterium. It will be 2.24 mega electron volt per c squared. And the binding energy for deuterium is nothing but delta M times c squared. It will be 2.24 mega electron. Another example, tightly bound alpha nuclides. Calculate the binding energy per nucleon of helium He42 alpha particle. The solution for helium, we have Z equal N equal to the total binding energy. As discussed, will be the binding energy will be the mass defect times c squared. It will be as such. Note that when U is 981.5 mega electron per c squared, then we find that the binding energy will be 28.3 mega electron volt, and hence the binding energy per nucleon is nothing but 7.07 mega electron volt. The binding energy per nucleon, as for lithium, we have to proceed the following steps. Let's calculate the mass defect at first, looking for the protons and the neutrons, and look for the conversion of mass from atomic mass unit to kilogram. And then apply the formula mass energy relationship and look for the deriving the binding energy per nucleon. We look for Aston curve. Aston plot the graph of the binding energy per nucleon of various atomic nuclei in a curve called Aston curve. Look for the nuclear energy. The nucleus has a size of 10⁻15 meter. The nuclei are bound together by a strong force. This force is about 100 times greater than the electric force between two protons. Both protons and neutrons are affected by the strong force. The strong force is what binds protons and neutrons together in the nucleus. The strong force is a short-range force. Because protons and neutrons appear to act identically to the strong force, even though the protons is electrically charged, they are often considered to be interchangeable and are called nucleons or nuclear constituents. Only when the distinction is important do we call them protons and neutrons. The binding energy reasoning. The protons repel each other by what force and tend to make nuclear unstable. The neutrons act to screen the protons from each other, interface between them, making the nuclide stable. For effective screening, there needs to be more neutrons than protons. When protons and neutrons reach together, make bonds, they give up energy. The nuclear binding energy, the binding energy must increase with the number of nucleons because to get more together, they must collectively give up a large amount of energy. This is called the binding energy of increasing Z that increases the number of protons. Upon studying the curve, we distinguish for A between 1 and 20, the binding energy per nucleon is less than 8 mega electron volt. Stability is somehow. Between 20 and 190, the binding energy is greater than 8, which is the most stable nuclei abundant found in nature. They are abundant. For A greater than 190, the binding energy returned back to be less than 8 mega electron volt. This is the degree of stability curve. Special features of the binding energy curve. Binding energy per nucleon of very light nuclei such as deuterium is very small. Initially, there is a rapid rise in the value of the binding energy per nucleon. Between the mass numbers 4 and 20, the curve shows cyclic recurrence of peaks corresponding to helium He42, Be84, and Ce12-6, and O18-6, and Ne2010. This shows that the binding energy per nucleon of these nuclides is greater than those of their immediate neighboring. Each of these nuclei can be formed by adding an alpha particle to the preceding nuclei. After A equal 20, there is a gradual increase in the binding energy per nucleon. The maximum value of 8.8 mega electron volt is reached at A equal 56. Therefore, iron nucleus is the most stable nucleus. Binding energy per nucleon of nuclides having mass numbers ranging from 40 up to 120 are closer to the maximum value. So these elements are highly stable and non-radioactive. Beyond A equal 120, the value of the decrease and fall is to 7.6 mega electron volt of uranium. Beyond A equal 128, the values shows a rapid decrease. This makes the elements beyond uranium etc. They are quite unstable and radioactive. Thank you for your listening.